good, but Flink is, in my opinion, is still the best open source stream processing system that you can use, and a ton of companies are using Flink in production since quite a few versions back. So yesterday there was a Flink conference also in San Francisco, and there a lot of companies talked about how they are productionizing Flink within their company. So that's it's complaining on a high level, if you wish, for the stuff that we have to work on is good stuff they want to add. So maybe Flink is already good, but there's more cool stuff coming, if you will. That's it. So I am the design specific, so I run a little team there called the Global Optimization Team. It's kind of focused on optimization across team boundaries, across organizational boundaries, across like sort of business, just as a bit of context. So first thing I want to say is optimizing Spark. I'm mostly talking about parallel computation in general, a few examples from Spark. So the first sort of disclaimer, if you've thought about this at all, you probably won't learn anything from me today. So I had an office mate in grad school that used to say the key to happiness is low expectations, so try to set them very low. If you haven't thought much about this, then my goal in the next 10 minutes is to give you a few sort of principles to organize your thinking. So the first principle is know what you want to measure, because this is so obvious, but you probably don't want to measure runtimes. At least it's not the thing that you want to care about. Of course, anytime you're trying to characterize the performance of something, you're going to be measuring runtimes somehow. But you don't just want to stop at saying, okay, the job runs faster, the job runs slower. You actually want to boil that down into something more meaningful. So the thing that you actually want to measure is the effective performance of some machine characteristics. So network bandwidth, file access latency, CPU operations per second, because that's how you're going to get to something where you feel you're sort of develop a natural understanding of what's going on, as opposed to just, well, we flip this switch, the runtime goes up, the runtime goes down. So how do you actually do this? You do this with carefully constructed data sets. So the idea is to measure network bandwidth. You want to construct data sets. The thing that changes is the network bandwidth requirements. So in this case, you want to construct a data set with the exact same number of files. The latency, whatever the latency comes from this drive, it's going to be the same. It does exactly the same operations. So the CPU performance also remains the same. And finally, if you want to, so here's what bandwidth works in.
高田の馬場経由で。
お客様、繰り返すか。はい、どうぞ。見せないとダメですよ。こっちが見えなかったら意味ないですよ。
高田の馬場経由で。
見せてくださいよ。
高田の馬場経由で。
高田の馬場経由。
はい。
これ高田の馬場までありますよ。
はい。
はい。160円ですね。はい。200円です。40円です。
あ、すみません。
Decommissioned Spark 2.0 at Stitch House, and everything was fine. But we also go through this process of what exactly is going wrong, at least identifying that it's something intrinsic to Spark 2.0. We wouldn't have necessarily known without having this kind of visibility. All right, so shifting gears a little bit. So this is more the sort of time versus money question. How do you know if you're getting your money's worth out of parallelization? So this is another real-world example. I mean, there are Spark. Oops, okay, I keep hitting the wrong button. There we go. There are different lines for different versions of Spark. That's not what I want to point out here. So this is again number of cores on one executor. So it's some measure of parallelism, and this is just the overall runtime of the job. So this is probably, if you're trying to characterize parallel performance, this is probably the first plot that you draw. It also doesn't really tell you anything about what you should do. I mean, it looks pretty good. Like, okay, should we run with 1 core per executor or 2 cores per executor? That looks like a pretty good difference in runtime. That's a decision. Okay, we probably want at least that much parallelism. Here, going from 4 to 8, there's almost no difference in runtime. So I've taken twice as many computers, let them run for the same amount of wall clock time, just to get to the same answer. So that definitely isn't buying me anything. So at least in 2 cases, like this feels probably pretty good to go from 1 to 2. Going from 4 to 8, definitely not. What about this one? This is an intermediate case. It runs a little faster, but is it worth it? So that's the thing that I want to think a little bit harder about. So the thing you actually want to do to characterize performance and make an informed decision is be really crisp about what are the costs and what are the benefits. So here what I have is cost. In this case, I mean, that's memory constrained, so at least most jobs are memory constrained, so this is actually gigabyte hours. But it's a measure of the total computational volume. This could just as well be CPU hours. If you're running AWS and things, I mean, that's the thing that's billed, right? So this could be dollars, which is the thing you actually want to measure your cost in. So here what we see is as you increase the number of Spark executors for this case, costs generally go up. So in a perfect world with linear speed up, so if I double the number of executors, my wall time comes down by a factor of 2. I want to ask how many CPU hours did I consume in total, it's the same. So that's a sort of, in a perfect world with linear speed ups, cost is independent of parallelism. But in the world that we actually live in, generally the costs go up. So that's to say, if I want to minimize my AWS bill, I should be down here, I should have as little parallelism as possible, and that will result in me writing the smallest check to Amazon. But what is the benefit of parallelism? So it basically allows you to get answers faster. So the way that I like to characterize this is 1 over the wall clock time. This basically tells you how many answers per hour can I get. So this translates either into I have an ad hoc query, I want to know the answer in an hour instead of a day, so that I can report back on that. Or in the context of a debug cycle, this is how long do I have to wait before I find out how and why my query failed, or how and why it didn't process the data exactly the way I thought. So in the context of a debug cycle, you want that to be as fast as possible. So good. So now we've characterized costs and benefits. It's worth lingering for a minute on, this is kind of a weird function. So if your job runtime is 1 hour versus 2 hours, that's probably not a big deal. Like, if a job runs for an hour, I have to go find something else to do for that hour. I can probably do that thing for 2 hours and then check on the job when it's done. It doesn't make a material difference to my day. Let's say that your job runs for 1 week versus 2 weeks. That probably is a big deal, because I mean, 2 weeks is a long time to tell somebody, I'm sorry, I can't have an answer for you for, until 2 weeks from now. 1 minute versus 10 minutes, especially in the context of a debug cycle, is a huge deal. If I have 1 minute to wait, I can, sort of think of something to do. If my job takes 10 minutes before I find out whether it succeeded or failed, I'm probably going to get distracted, go off and do something else. So the point here is that once we're crisp on costs and benefits, you'll be in a position to say things like this. If I double the amount of parallelism in my job, my AWS bill will rise by 30% and the job will run in 45 minutes instead of 60 minutes. Does that feel worth it to me? So that's the sort of crucial question at the end of the day that you want to be able to answer to make an informed decision. Alright, so recap. So when you're characterizing parallel performance, you want to focus on measuring things that are intrinsic to the machine somehow. So you want to measure your effective network bandwidth, your effective file access latency, things like this. In order to do this, the way to do it is use carefully constructed data sets to change one and only one thing. And then if you're trying to figure out if you're getting your money's worth out of the amount of parallelism that you're using currently, if you want to know whether you want more parallelism or less parallelism, you need to be crisp on costs, which are basically dollars, and benefits, which are essentially debug cycles per hour, and then you can make informed choices. That's it. Thank you.
Hi everybody, I'm Eugene. I work on the Google Cloud Dataflow and Apache Beam teams. I've been doing that for a few years, and I think it's a pretty good piece of work, so now I'm going to give you a really quick overview of the several core things that one needs to know about Beam. First, a little bit of history. It originated back in 2004 when Google created MapReduce, which was a distributed data processing programming model, but at its core, it's really just a huge select and a huge group by, and nothing more. It just does it really well in a distributed and fault-tolerant fashion. It evolved into directions pretty quickly. People realized that one select and one group by is not that useful, and it's better to build a high-level API where you can build whole graphs made of that, and that's what Flume Java did, and that is also the programming model familiar probably to people who use Spark or Flink. So pretty much all distributed data processing frameworks are in some way based on these two primitives, parallel by and parallel group by. The other direction in which it evolved was Millwheel, a streaming processing system also created inside Google, whose focus was to disrupt the idea that streaming data processing has to be approximate. Millwheel aimed to make it deterministic and exact. And the core idea behind that was to do computations based on the absolute time when certain events happened as opposed to when this particular processing pipeline saw them. Then in 2014 these things were unified into Cloud Dataflow, which unified batch streaming under one programming model that I will explain soon, because Beam uses that programming model. And Dataflow from the beginning aimed to become portable between different runners. So the point was that you can run these pipelines on more than just Dataflow. And in 2016 this culminated in the creation of Apache Beam, which is a top-level Apache project with an open ecosystem. It's not critically dependent on any particular vendor. For example, less than half of the committers are even from Google, and it's community-driven. So this is just a high-level context, and this is an example code with Beam. It should be pretty readable for anybody who uses any data processing framework, so I'm not going to go into too much detail into it. There is two concepts. There is collections, which represent logical sets of data but don't really contain the data, and there is transforms that take collections as input and produce collections as output. Simple enough. So all Beam pipelines are composed of three primitives. There is parallel do, which simply applies the function parallel to every element. There is parallel group by, that takes a collection of elements and groups them by a key and produces a collection of groups that share the same key. And these can be grouped into higher level